What is logic? Logic, from classical Greek lambda gamma omicron, logos, originally meaning the word, or what is spoken, but coming to mean thought or reason or an explanation or a justification or key, is most often said to be the study of criteria for the evaluation of arguments, although the exact definition of logic is a matter of controversy among philosophers. However the subject is grounded, the task of the logician is the same, to advance an account of valid and fallacious inference, in order to allow one to distinguish good from bad arguments. Traditionally, logic is studied as a branch of philosophy. Since the mid-1800s, logic has also been commonly studied in mathematics, and, more recently, in set theory and computer science. As a science, logic investigates and classifies the structure of statements and arguments, both through the study of formal systems of inference, often expressed in symbolic or formal language, and through the study of arguments in natural language, a spoken language such as English, Italian, or Japanese. The scope of logic can therefore be very large, ranging from core topics such as the study of fallacies and paradoxes, to specialist analyses of reasoning such as probability, correct reasoning, and arguments involving causality. Nature of logic. Because of its fundamental role in philosophy, the nature of logic has been the object of intense dispute. It is not possible clearly to delineate the bounds of logic in terms acceptable to all rival viewpoints. Despite that controversy, the study of logic has been very coherent and technically grounded. In this article, we first characterize logic by introducing fundamental ideas about form, then by outlining some schools of thought, as well as by giving a brief overview of logic's history, an account of its relationship to other sciences, and finally, an exposition of some of logic's essential concepts. Informal, formal, and symbolic logic. The crucial concept of form is central to discussions of the nature of logic, and it complicates exposition that the term formal in formal logic is commonly used in an ambiguous manner. We shall start by giving definitions that we shall adhere to in the rest of this article. Informal logic is the study of arguments expressed in natural language. The study of fallacies, often known as informal fallacies, is an especially important branch of informal logic. An inference possesses a purely formal content if it can be expressed as a particular application of a wholly abstract rule, that is a rule that is not about any particular thing or property. For example, the argument, if John was strangled he died. John was strangled, therefore John died, is an example, in English, of the argument form or rule, if P then Q, P is true. Therefore Q is true. Moreover, this is a valid argument form, known, since the Middle Ages, as modus ponens. We will see later that on many definitions of logic, logical inference and inference with purely formal content are the same thing. This does not render the notion of informal logic vacuous, since one may wish to investigate logic without committing to a particular formal analysis. Formal logic is the field of study in which we are concerned with the form or structure of the inferences rather than the content. Symbolic logic is the study of abstractions, expressed in symbols, that capture the formal features of logical inference. The ambiguity is that formal logic is very often used with the alternate meaning of symbolic logic as we have defined it, with informal logic meaning any logical investigation that does not involve symbolic abstraction. It is this sense of formal that is parallel to the received usages coming from formal languages or formal theory. While formal logic is old, on the above analysis, dating back more than 2 millennia to the work of Aristotle, symbolic logic is comparatively new, and arises with the application of insights from mathematics to problems in logic. The passage from informal logic through formal logic to symbolic logic can be seen as a passage of increasing theoretical sophistication. Of necessity, appreciating symbolic logic requires internalizing certain conventions that have become prevalent in the symbolic analysis of logic. Generally, logic is captured by a formal system, comprising a formal language, which describes a set of formulas and a set of rules of derivation. The formulas will normally be intended to represent claims that we may be interested in, and likewise the rules of derivation represent inferences. Such systems usually have an intended interpretation. Within this formal system, the rules of derivation of the system and its axioms, see the article axiomatic systems, then specify a set of theorems, which are formulas that are derivable from the system using the rules of derivation. The most essential property of a logical formal system is soundness, which is the property that under interpretation, all of the rules of derivation are valid inferences. The theorems of a sound formal system are then truths of that system. A minimal condition which a sound system should satisfy is consistency, meaning that no theorem contradicts another. Another way of saying this is that no statement or formula and its negation are both derivable from the system. Also important for a formal system is completeness, meaning that everything true is also provable in the system. However, when the language of logic reaches a certain degree of expressiveness, say, second-order logic, completeness becomes impossible to achieve in principle. In the case of formal logical systems, the theorems are often interpretable as expressing logical truths, tautologies, or statements that are always true, and it is in this way that such systems can be said to capture at least a part of logical truth and inference. Formal logic encompasses a wide variety of logical systems. Various systems of logic we will discuss later can be captured in this framework, such as term logic, predicate logic, and modal logic, and formal systems are indispensable in all branches of mathematical logic. The table of logic symbols describes various widely used notations in symbolic. While many cultures have employed intricate systems of reasoning, logic as an explicit analysis of the methods of reasoning received sustained development originally in three places: China in the 5th century BCE, Greece in the 4th century BCE, and India between the 2nd century BCE and the 1st century BCE. The formally sophisticated treatment of modern logic apparently descends from the Greek tradition, although it is suggested that the pioneers of Boolean logic were likely aware of Indian logic. Gannery 2001, the Greek tradition itself comes from the transmission of Aristotelian logic and commentary upon it by Islamic philosophers to medieval logicians. The traditions outside Europe did not survive into the modern era. In China, the tradition of scholarly investigation into logic was repressed by the Qing dynasty following the legalist philosophy of Han Fizi. In the Islamic world, the rise of the Asharite school suppressed original work on logic. However, in India, innovations in the scholastic school, called Nyaya, continued into the early 18th century. It did not survive long into the colonial period. In the 20th century, Western philosophers like Stanislaw Scheyer and Klaus Glashow have tried to explore certain aspects of the Indian tradition of logic. During the medieval period, a greater emphasis was placed upon Aristotle's logic. During the later period of the medieval ages, logic became a main focus of philosophers, who would engage in critical logical analyses of philosophical arguments, and who developed sophisticated logical analyses and logical methods. Topics in logic. Throughout history, there has been interest in distinguishing good from bad arguments, and so logic has been studied in some more or less familiar form. Aristotelian logic has principally been concerned with teaching good argument, and is still taught with that end today, while in mathematical logic and analytical philosophy much greater emphasis is placed on logic as an object of study in its own right, and so logic is studied at a more abstract level. Consideration of the different types of logic explains that logic is not studied in a vacuum. While logic often seems to provide its own motivations, the subject usually develops best when the reason for the investigator's interest is made. The Organon was Aristotle's body of work on logic, with the prior analytics constituting the first explicit work in formal logic, introducing the syllogistic. The parts of syllogistic, also known by the name term logic, were the analysis of the judgments into propositions consisting of two terms that are related by one of a fixed number of relations, and the expression of inferences by means of syllogisms that consisted of two propositions sharing a common term as premise, and a conclusion, which was a proposition involving the two unrelated terms from the premises. Aristotle's work was regarded in classical times, and from medieval times in Europe and the Middle East, as the very picture of a fully worked-out system. It was not alone. The Stoics proposed a system of propositional logic that was studied by medieval logicians. Nor was the perfection of Aristotle's system undisputed. For example, the problem of multiple generality was recognized in medieval times. Nonetheless, problems with syllogistic logic were not seen as being in need of revolutionary solutions. Today, Aristotle's system is mostly seen as of historical value, though there is some current interest in extending term logics, regarded as made obsolete by the advent of sentential logic and the predicate calculus. Predicate logic. Logic as it is studied today is a very different subject to that studied before, and the principal difference is the innovation of predicate logic. Whereas Aristotelian syllogistic logic specified the forms that the relevant parts of the involved judgments took, predicate logic allows sentences to be analyzed into subject and argument in several different ways, thus allowing predicate logic to solve the problem of multiple generality that had perplexed medieval logicians. With predicate logic, for the first time, logicians were able to give an account of quantifiers, expressions such as all, some, and none, general enough to express all arguments occurring in natural language. The discovery of predicate logic is usually attributed to Gottlob Frege, who is also credited as one of the founders of analytical philosophy, but the formulation of predicate logic most often used today is the first-order logic presented in Principles of Theoretical Logic by David Hilbert and Wilhelm Ackermann in 1928. The analytical generality of the predicate logic allowed the formalization of mathematics, and drove the investigation of set theory, allowed the development of Alfred Tarski's approach to modal theory. It is no exaggeration to say that it is the foundation of modern mathematical logic. Frege's original system of predicate logic was not first, but second order. Second-order logic is most prominently defended, against the criticism of Willard van Orman Quine and others, by George Bullows. In language, modality deals with the phenomenon that subparts of a sentence may have their semantics modified by special verbs or modal particles. For example, we go to the games can be modified to give we should go to the games, and we can go to the games and perhaps we will go to the games. More abstractly, we might say that modality affects the circumstances in which we take an assertion to be satisfied. The logical study of modality dates back to Aristotle, who was concerned with the alethic modalities of necessity and possibility, which he observed to be dual in the sense of De Morgan duality. While the study of necessity and possibility remained important to philosophers, little logical innovation happened until the landmark investigations of Clarence Irving Lewis in 1918, who formulated a family of rival axiomatizations of the alethic modalities. His work unleashed a torrent of new work on the topic, expanding the kinds of modality treated to include deontic logic and epistemic logic. The seminal work of Arthur Prior applied the same formal language to treat temporal logic and paved the way for the marriage of the two subjects. Saul Kripke discovered, contemporaneously with rivals, his theory of frame semantics, which revolutionized the formal technology available to modal logicians and gave a new graph-theoretic way of looking at modality that has driven many applications in computational linguistics and computer science, such as dynamic logic, deduction and reasoning. The motivation for the study of logic in ancient times was clear. As we have described, it is so that we may learn to distinguish good from bad arguments, and so become more effective in argument and oratory, and perhaps also, to become a better person. This motivation is still alive, although it no longer necessarily takes center stage in the picture of logic, typically dialectical or inductive logic, along with an investigation of informal fallacies, will form much of a course in critical thinking, a course now given at many universities. Mathematical logic really refers to two distinct areas of research. The first is the application of the techniques of formal logic to mathematics and mathematical reasoning, and the second, in the other direction, the application of mathematical techniques to the representation and analysis of formal logic. The boldest attempt to apply logic to mathematics was undoubtedly the logicism pioneered by philosopher-logicians such as Gottlob Frege and Bertrand Russell with his colleague Alfred North Whitehead. The idea was that, contra Kant's assertion that mathematics is synthetic a priori, mathematical theories were logical tautologies and hence analytic, and the program was to show this by means to a reduction of mathematics to logic. The various attempts to carry this out met with a series of failures, from the crippling of Frege's project and his Grundsätze by Russell's paradox, to the defeat of Hilbert's program by Gödel's incompleteness theorems. Both the statement of Hilbert's program and its refutation by Gödel depended upon their work establishing the second area of mathematical logic, the application of mathematics to logic in the form of proof theory. Despite the negative nature of the incompleteness theorems, Gödel's completeness theorem, a result in modal theory, and another application of mathematics to logic, can be understood as showing how close logicism came to being true. Every rigorously defined mathematical theory can be exactly captured by a first-order logical theory. Freya's proof calculus is enough to describe the whole of mathematics, though not equivalent to it. Thus we see how complementary the two areas of mathematical logic have been. If proof theory and model theory have been the foundation of mathematical logic, they have been but two of the four pillars of the subject. Set theory originated in the study of the infinite by George Cantor, and it has been the source of many of the most challenging and important issues in mathematical logic, from Cantor's theorem, through the status of the axiom of choice and the question of the independence of the continuum hypothesis, to the modern debate on large cardinal axioms. Recursion theory captures the idea of computation in logical and arithmetic terms. Its most classical achievements are the undecidability of the Entscheidungsproblem by Alan Turing, and his presentation of the Church-Turing thesis. Today recursion theory is mostly concerned with the more refined problem of complexity classes. When is a problem efficiently solvable, and the classification of degrees of unsolvability. Philosophical logic deals with formal descriptions of natural language. Most philosophers assume that the bulk of normal proper reasoning can be captured by logic, if one can find the right method for translating ordinary language into that logic. Philosophical logic is essentially a continuation of the traditional discipline that was called logic, before it was supplanted by the invention of mathematical logic. Philosophical logic has a much greater concern with the connection between natural language and logic. As a result, philosophical logicians have contributed a great deal to the development of non-standard logics, e.g., free logics, tense logics, as well as various extensions of classical logic, e.g., modal logics, and non-standard semantics for such logics, e.g., Kripke's technique of supervaluations in the semantics of logic. Logic and computation. Logic cut to the heart of computer science as it emerged as a discipline. Alan Turing's work on the Entscheidungsproblem followed from Kurt Gödel's work on the incompleteness theorems, and the notion of a general-purpose computer that came from this work was of fundamental importance to the designers of the computer machinery in the 1940s. In the 1950s and 1960s, researchers predicted that when human knowledge could be expressed using logic with mathematical notation, it would be possible to create a machine that reasons, or artificial intelligence. This turned out to be more difficult than expected because of the complexity of human reasoning. In logic programming, a program consists of a set of axioms and rules. Logic programming systems such as Prolog compute the consequences of the axioms and rules in order to answer a query. Today, logic is extensively applied in the fields of artificial intelligence and computer science, and these fields provide a rich source of problems in formal logic. The ACM computing classification system in particular regards Section F.3 on logics and meanings of programs and F.4 on mathematical logic and formal languages as part of the theory of computer science. This work covers formal semantics of programming languages, as well as work of formal methods such as Hoare logic. Boolean logic is fundamental to computer hardware, particularly the systems section B.2 on arithmetic and logic structures. Many fundamental logical formalisms are essential to section I.2 on artificial intelligence, for example modal logic and default logic in knowledge representation formalisms and methods, and horn clauses in logic programming. Furthermore, computers can be used as tools for logicians. For example, in symbolic logic and mathematical logic, proofs by humans can be computer-assisted. Using automated theorem proving the machines can find and check proofs, as well as work with proofs too lengthy to be written out by hand.